When we talk about linear independence of a set of vectors, there are some things we will need to look at. So let's look at this first set. Here's a set with 1, 2, 3, 4, 5 vectors. If we want to name them, we can name them V1, V2, V3, V4, and V5. Now if we're going to make an observation about this set, we can very quickly see that V3 is just 2 times V1. You should be able to see, or with a bit of investigation, that V1 plus 2 times V2, V1 plus 2 times V2 will give me V4. And a more complicated relationship that you can't necessarily see, but you can check that, is that V1 minus 2 times V3 plus 3 times V4 is going to give me V5. Now, what does this say? This means that some of the vectors in this set, for example, V3, I can generate V3 looking at linear combinations of some of the other elements, for example, V1. I can generate V5 looking at linear combinations of V1, V3, and V4. Now, that intuitively, and we're going to get the formal definition shortly, means this set is linearly dependent. Because what this means is some of the elements of the set can be written as linear combinations of the other elements of the set. So that is what we're going to use to test and to look at linear independence or dependence, but we've got to formally define it first. So the formal definition of linear independence says that if I've got a set of vectors and scalars, then this vector equation, so linear combinations of all the vectors in S, if I set that equal to the 0 vector, normally that has at least one solution. All right, we know that a homogeneous system has one solution at least, which is the trivial solution, but it could have more solutions. So what we're saying is if this vector equation has only one solution, the trivial solution, then the elements of those sets is linearly independent, or we say the set is linearly independent. But if there's more than the trivial solution, the set is linearly dependent. So let's look at a very simple example, I, j, and k. If we look at I equal to 1, 0, 0, j equal to 0, 1, 0, and k equal to 0, 0, 1. The set with those three elements, if you look at them, you can see I cannot get to one of them using the other two. I cannot use linear combinations of two of these elements to get to the other one. But now let's measure this against the formal definition. So if I say let C1, C2, and C3 be real numbers, and I consider the vector equation C1 times I plus C2 times j plus C3 times k. If I look at that vector equation, setting it equal to the 0 vector, I want to show that it has only the trivial solution. Then I can say that that set S is linearly independent. So let's see. What would the system of equations look like? I would have C1 plus 0 is equal to 0. I will have C2 is equal to 0 and C3 is equal to 0. This is a very simple one. Very obviously, this vector equation, the system of equations that's generated by the vector equation, has only the trivial solution. So because the vector equation has only the trivial solution, the system of equations linked to that vector equation, then I can say that the set, therefore S, is linearly independent. And what that means is those three stand alone. Not one of them is a linear combination of the others. All right, so let's look at this set. If I've got a set with vectors V1, V2, and V3 in, so if I say let S be the set with V1, V2, and V3 in, is this set linearly independent? Well, we're going to let K1, K2, and K3 be real numbers. And we're going to consider the vector equation K1 times V1, which is 1, 1, 2, plus K2 times 1, 0, 1, plus K3 times 2, 1, 3, equal to the 0 vector, 0, 0, 0. And we want to know, does this system generated from this vector equation have only the trivial solution? Let's look at the system. The system of linear equations is then K1, look at the first entry, K1 plus K2. Sorry, this is a multiplication, plus 2K3 is then equal to 0. K1 plus K3 is equal to 0. 2K1 plus K2 plus 3K3 equal to 0. Now this one is not so easy. The previous one, the answer just popped out. So let A be the coefficient matrix of the system. Now we know from our previous work, if the determinant of A is 0, then AX equal to 0 has only the trivial solution. So I want to look at the determinant of A, which is the determinant of the matrix 1, 1, 2, 1, 0, 1, 2, 1, 3. If I look at the determinant of that matrix, I want to know, is it 0 or isn't it? If the determinant of A is 0, then I've got non-trivial solutions. If the determinant of A is non-zero, then I have only the trivial solution. So you can use any row or column with cofactor expansion and calculate the determinant, and you will see the determinant is 0. Now what does that tell me? The determinant of A being 0, I can't just jump straight to linear dependence and independence, because this determinant tells me something about the solutions to the system. So therefore, the system has non-trivial solutions. And if the system has non-trivial solutions, I can now make a conclusion about the set. S is linearly dependent. So that's the process we're going to follow. We're going to look at the vectors, measure it against the definition of linear dependence and independence, meaning look at solutions to this vector equation. If it has only the trivial solution, then it's linear. The set is linearly independent. If it's got other solutions, non-trivial solutions, the set is linearly dependent.